right, so guess I should put that up. Cool, all right, so just to kind of review what we've been talking about with chapter 6, right, I started off by introducing this concept of nucleophiles and bases, both of which are electron-rich species, but they play different roles in reactions, right? So kind of the Cliff Notes version of what we've covered thus far here. When we have our molecule playing the role of a nucleophile, that means it's doing one of these substitution reactions, right? So you're swapping functional groups. You're swapping your leaving group for the nucleophile, right? So that's what a nucleophile is. It's playing a role in these substitution reactions. And we have these two different mechanisms for our substitution reactions. The big difference between them is with the Sn2, you have an inversion of your stereochemistry, and with the meaning that you got to switch your wedges to dashes and vice versa, right? And then with the Sn1, there is no inversion of stereochemistry. So you got to draw both products with the wedge and the dash, right? That's the big difference between those two mechanisms. We can look at them in terms of their electron pushing arrows, and that explains why this is, but again, y'all can just trust me on that also, right? We don't really have to have these mechanisms memorized or anything like that. So different compounds will undergo either one of these mechanisms. If it's a primary or secondary carbon, that's when it's Sn2, and the tertiary carbons do the Sn1. All right, and these were these substitution reactions. When it's participating in what we called an elimination reaction, that's when it's playing the role of a base, right? Bases accept protons. The product of these elimination reactions are these alkenes, and it's always the more highly substituted alkene that's formed, right? So if you have multiple alkenes that could be formed, you always are going to pick the more highly substituted one. There are two different mechanisms, E1 and E2 for this, but they both lead to the same product. Okay, so we do have to know, when we built our little chart, we know which ones undergo E1 and E2, but in terms of drawing our products, we don't really have to consider it like we do the Sn1 and the Sn2. All right, and then I told you I'd give you this chart here, which tells you what's a good nucleophile, what's a bad nucleophile, what's a good base, and what's a bad base. All right, and then we tied this all together because we built this little chart here. So I'm going to go through and do it again just to kind of make a point. Okay, and so again, you'll be given the list of good nucleophile, good base, all that sort of jazz. But this chart down here is what we got to know, right? How to use this information. Oh my gosh. Okay, so starting off with like this category here, strong base but bad nucleophile, right? That means that it's going to prefer only those elimination type reactions because it's a poor nucleophile. So this category for all primary, secondary, and tertiary are all elimination reactions, and specifically those E2 type elimination reactions. Okay, kind of skipping around, I'm going to jump to this category here. These are now compounds that are bad bases but good nucleophiles, right? So they're only going to be doing substitution reactions. So like we said, primary and secondary undergo Sn2 type substitution reactions where we got to flip our wedges and dashes, and then the tertiary do the Sn1. All right. Weak nucleophiles and weak bases. These don't do anything to primary or secondary carbons, but if you have a tertiary carbon, you're going to get an even mixture of Sn1 and E1 reactions. Right? So you get both the substitution and the elimination product in pretty much a 50-50 mixture. There's not one that we declare as the major product. All right? And then the trickiest one, I think, is what happens when you have both a strong nucleophile and a strong base. In this category, the primary will still undergo substitution reactions, okay? But the secondary and tertiary will instead undergo elimination reactions. All right, and it just has to do, the reason why is just because, let's say that we have two compounds, one of them's primary and one of them's secondary. In a primary, that carbon that you're substituting, that what we call the electrophile, is really easily accessible because it's kind of sticking out right on the end there. Whereas if you have a secondary or a tertiary, it's a little bit more buried. It's a little bit harder for the nucleophile to get to. So that's why in this particular category, the substitution is only for the primary, whereas secondary and tertiary undergo elimination reactions. All right, so again, just to kind of color code our little chart, these are the elimination reactions. You can see it makes like a little bit of a staircase, which hopefully will make it easier to remember. Okay, and there are substitution, but then again, this category is kind of the odd man out in that it's the mixture of the two. All right, so again, I'll give you this one at the top, and this is the information at the bottom that you got to know. This is how we kind of use this chart. All right, and I said today, all we're going to do is just practice using this chart over and over and over again. Practice looking at reactions over and over again. All right. One, so we can get good at it, and two, so we can make sure to put eyes on what each of these individual things down here actually look like when we draw them out, right? So that they kind of look a little bit familiar. All right, so again, this chart here, you definitely want to make sure you have in your notes. So yeah, if you have not already, make sure when we're going through this, make sure to get that in there, because at some point I'm going to put up a bunch of different examples. I'm going to have to move away from this page, but let's just do a few real quick, ones that are similar to what we've done thus far. All right. So for each one, I'm going to put one down, like kind of give you a second to try to get predict the products on your own, and then I'll go in and do it. Bless you. All right, so first of all, we got to classify our alkyl halide as primary, secondary, or tertiary. Which one is this one going to be? All right, so again, what we're going to do is we're going to look at the base of that halogen, and we're going to count how many neighbors, how many carbon-carbon neighbors it has. In this case, there are 2, so it's secondary. Now I'm going to look at my reagent here. Do you guys remember what I told you to do whenever you see sodium? Yeah, you sort of erase, in your mind, you're going to erase it and replace it with a negative sign, because that's what sodium's doing. It's really forming this ionic compound. It's just our counter ion. It's not actually participating in the reaction whatsoever. So really, it's the iodide ion that's going to be doing the reacting here. So that puts us in this category here, our weak base strong nucleophile, which means that we have an Sn2 reaction on our hands here. Sn2, is that where I flip the stereochemistry or don't flip the stereochemistry? Flip it. All right, so in this case, my product would be the substitution product with that stereochemistry inverted. All right, I wouldn't draw both of them. I would just draw this one with the stereochemistry inverted. All right, I've substituted out my bromide for my iodide. So if I was being really good at balancing my equation, I would also put the bromide ion. But again, what you're going to find is that we get really lazy in organic chemistry. We really only care what's happening to those carbons. So oftentimes when you see this, you won't even see the bromide written, right? It's off floating around somewhere. Nobody cares. Okay, but so this is the name of the game here, using this chart and predicting products. Got to identify whether you got a primary, secondary, or tertiary substrate, and then find your nucleophile / base in whatever category it belongs in. Cool, all right. This is a tricky one. All right, so how many products should I have drawn? All right, so let's look real quick. So first of all, what's the category that my substrate falls into? Primary, secondary, or tertiary? All right, so I'm gonna look at this carbon at the base of my leaving group, and I'm gonna count how many carbon neighbors it has. 1, 2, and then this one over here on this wedge makes 3. So this would be a tertiary substrate. And then what category does my alcohol here, my ethanol, fall into? Okay, so this is what this is right here. ETOH means ethanol. And really, you know, I'm going to go in and I'm going to replace these two here with ROH, because it's really anything that has an OH group. It doesn't matter how many carbons there are on the back end there. In this case, I have 2 carbons drawn. Really doesn't matter if there were 400 carbons. It would be the same type of reaction. Okay, so that means I'm in this category right here, my Sn1 and E1 reactions. So I got an Sn1 product and my E1 product. All right, so let's do the E1 first, my elimination. What's important to sort of see with your elimination products is definitely the carbon that I've highlighted here in red is going to have the double bond on it, right? But then the question is, which one of these other carbons does that double bond form between? And again, it's going to be the more highly substituted alkene that's formed. So I have 2 options. Can either be this one here, or this one here, right? Which one of those 2 is it going to be my actual elimination product? The one on the left or the one on the right? And the one that's more highly substituted, right? This one here. So my actual elimination product is this one here. Here's my E1 product. All right, if you left this as a wedge, that's cool. I'm not gonna, you know, Truthfully, it should be just drawn as a straight line because if you remember back to when we were discussing alkenes, all of these are lying in the same plane. We talked about the geometry of alkenes, so it wouldn't actually be a dash or a wedge. To be honest, I'm not going to be too butthurt about it if you did leave it as a wedge, okay? So that's my E1 product, right? And I also have to include my Sn1 product. But for Sn1, am I going to flip it, or is this where I have to draw both? This is where we have to draw both, right? So in fact, you should have 3 products at the end of this reaction. 2 of them are our substitution product, and 1 of them is the elimination product, right? If we go back to our little cheat sheet here, we have no inversion of stereochemistry, which means that we're going to get both the dash and the wedge substitution. All right, that's what we got to know about our Sn1 reactions here. This is our little cheat sheet. When it's Sn2, we just have the 1 product where the stereochemistry is inverted. When it's Sn1, we have to draw both. Okay, so the first one I'm going to do, I'm going to just replace my leaving group with my nucleophile here, and I'll keep it as a wedge. Or rather as a dash, okay, and then note this is what it looks like when it's, well, that's not what I meant to do. This is what it looks like when it's substituted on there. I lose that hydrogen, it's just the oxygen. All right, this category right here, these weak base, weak nucleophiles, they can be hard to see what's going on because, again, you're going to be losing one of those hydrogens. When we looked at the mechanism, we saw that one of the last steps was losing that hydrogen from our nucleophile. Remember, we created this kind of little cheat sheet last time where whether you're using a OH group or water as your substrate, they both come on as just OH groups. Right? In each case, your weak nucleophile here is losing a hydrogen when it's being put on there. So if it starts out with a negative charge, it's a little bit more straightforward to get your substitution product. But when it starts out neutral, it's going to lose a hydrogen when you put it on there. Okay? So again, we're just going to practice the crap out of this. So everybody take a second and draw me my second substitution product here for this reaction. Again, you got to give me both. This is the one where it's on the dash. Now you got to give me the one where it's on the wedge. All right, so again, for my Sn1 product, I have to draw both of these as my substitution product, where my new functional group is on a wedged bond in one and where it's on a dash bond in the other. If you had like swapped the position of the wedged bond, so you had your wedge pointing this direction and your dash pointing that direction, that's fine, it's the same thing, right? What's important is that you have the functional group on a wedge and a dash. You have these two products as your substitution product. That's the difference between an Sn1 reaction mechanism and the Sn2 mechanism. All right, for the Sn1, we got to draw both. Okay? All right, so first of all, what am I going to do to that sodium? Erase it and then replace it with a negative sign. Okay. For my substrate, primary, secondary, or tertiary? So this is primary. And then which category does my nucleophile / base live in? So this is this one right here. So this is the strong base, weak nucleophile. So no matter what my substrate is, I'm always just going to get the elimination product in this category. Okay. Primary, we're going to see, are kind of the easiest to deal with. In this case, there's only one option for where my double bond can be formed, and that is between these two carbons here. That's the only possibility. So my E2 product here would be this alkene. Okay, I'm going to keep this same nucleophile / base, but now I'm going to use this substrate. So everybody take a second and see if you can draw me my product. What's my mechanism? Sn1, Sn2, E1, E2. So this one would be the E2, right? Because now I'm this category right here. Oh, that's a 2, believe it or not. Okay, and importantly, the alkene that's going to form is the more highly substituted, right? So it's not going to form, right? I had two possibilities. It could have been on the end here or in the middle. Again, the more highly substituted alkene is the one that's going to be your product. So this is my product here. Okay, let's take a look at some of these weirder looking ones. We'll actually keep that same substrate. But now let's use what am I going to do to that sodium? All right, replace it with the minus sign. So see if you can't find where this would be in our little list here. This is probably one of the harder functional groups to spy on our list. Anybody got it? It is not strong base, strong nucleophile. So this thing here is this. RCOO minus. Right? This is the R. However long this sort of carbon chain is, here is my R. Here's the COO with the minus sign. Not that it really matters, but this is what we call a carboxylate. Anyways, this thing right here with the oxygen double bonded and then the other oxygen with the single bond and the negative charge, again, this corresponds to this thing right down here in this category. Okay, again, probably the hardest one to spy off of our list here, so let's make sure that we can see that. All right, so now that we know what category it is, everybody take a second and draw me my product. It's going to be very weird and ugly looking. All right, because you're going to have this oxygen now attached to this carbon. But you're going to have everything on the back end of it too, that carbon-oxygen double bond, all that other stuff. All right, so everybody take a second and see if you can't draw me what my product would look like in this Sn2 substitution reaction. All right, if you draw it out and you're like, nah, this doesn't look right, I sympathize with you, but in fact, that big ugly thing is indeed our product. All right, so I'm going to start with my 4 carbons in my substrate. Those are definitely going to be there. This is the substitution product, so I'm going to swap out my leaving group for my nucleophile here. But since it's Sn2, what am I going to make sure to do to that bond? Make it inverted, exactly. Make it a dash, right? Because it's a wedge on my reactant side, so that means it needs to be a dash on my product side. Okay? And then I essentially got to attach this whole thing over here, right? That's the name of the game. So there's an oxygen. That oxygen has that carbon bound and that other carbon. All right, so let's just take a second. Everybody stare at this for a second and make sure that they can convince themselves that this chunk here is indeed the same thing as this chunk here. All right, I've just substituted on that nucleophile. Again, I know it's big and ugly. Yeah, I hear you. What's up?
So we don't take off, I think because it's a bigger molecule, it's kind of confusing.
No, totally, I get that.
Take off the bond to the negative oxygen.
Right, so this oxygen here is what's going to end up being attached. This oxygen here is what gets attached to this carbon here. And I know that it looks weird, and again, she's absolutely right. It looks very weird because it's a much bigger molecule, so your brain is like, what the heck is going on here, right? But it's really no different than when I just had it as an OH minus. And we attached it, right, when it was an OH minus. Again, we put that oxygen on there. We had our oxygen now bound to our carbon. Same idea, it just takes all that other crap on the back end with it as well. That carbon-oxygen double bond. All right, so in both of these examples here, I'll color code this one with a different color. You have your oxygen.
So the negative oxygen is what attaches?
Correct. Just like when we had the hydroxide ion, it was that negative oxygen that attached to our carbon. And you got to flip the stereochemistry specifically because this was that Sn2 category.
So the carbon isn't the one that's attaching.
Correct. It's not this carbon right here is not attaching itself. No, it's that oxygen that I've highlighted in green. Just like when it was the OH group, it was this oxygen that I highlighted in orange that got attached. All right, let's just practice the crap out of it until it looks familiar. That's a good question.
there's no stereochemistry.
You just don't have to worry about it. You don't have to worry about dashes and wedges. If you don't see any dashes and wedges, then you don't have to worry about it. All right, I know this stereochemistry thing is weird. Truthfully, we jumped over chapter 5, which is sort of focuses on stereochemistry. Stereochemistry is the dumbest thing to teach to non-majors in the entire world. It is so overly complicated that I just felt like it was so stupid to try to introduce. So essentially, just trust me. You flip dashes to wedges, and we call that stereochemistry. Okay, whether it's a dash or a wedge. We're not going to learn the whole logic behind it. It's ridiculous. All right. It sucks even for the two semester course. Stereochemistry is the worst topic for everybody. So we're not gonna, I don't know. We don't need to overly complicate things here. We can do the fun puzzle stuff like this. I know fun is probably not the word that you would use, but. All right, so first of all, what's my mechanism? Sn1, Sn2, E1, E2. Sn2, because we got a primary, and again, this is this thing right here. So we have an Sn2. So I'm going to start off with my substrate, my 3 carbons. And again, it's this carbon here that's getting my new functional group. This sodium, I'm going to erase it, put a negative charge. Okay, and again, it's this oxygen here that's going to get attached to my red carbon that I colored. Right, so oxygen with a carbon, and I'm going to make sure to include 1, 2, 3, 4 carbons on the back end here. So 1, 2, 3, 4 carbons. So 2 different things, right? I start out with 3 carbons on my substrate. That were these 1, 2, 3 over here. But I also got to make sure to include the 4 carbons, 1, 2, 3, 4, that were on my nucleophile. 1, 2, 3, 4. Right. Fun fact, you guys don't have to worry about this like for the exam or anything, but this is what we would call an ester. These are actually the compounds that are like fruity smelling. So for example, this compound here specifically smells like apples. All those like bananas have their own esters. Pears have their own esters. These are molecules that give fruits their fruity smells. All right, let's pull it back a little bit. Do one that's not quite as bad looking. So R means any carbons, like a carbon chain of any length. So R2N with the negative sign would be nitrogen that has a minus sign, and then any amount of carbons on there.
You have to have like 2 attached to the nitrogen.
It could, one of them could be just a hydrogen as well. So there's kind of a lot that would fit into that category. let me draw it all the same way. So H2N minus, if we had like CH3, 2N minus. Basically, anytime you see a nitrogen with a negative charge on it. Super strong bases, but also very good nucleophiles. Okay, so what category do I fall into here? I'm sorry, what category does my reagent, my NaSH, fall into? All right, so that's this thing, right, where is it? Nope, this one right here. So this tells me that I'm going to have an Sn2 reaction. So I'm going to draw my substitution product, and I'm going to make sure to flip that dash bond to a wedge.
Why is it not the RSH? Like one next to
It kind of is. I mean, R could be anything, you know.
No, like the other one to the right.
Yeah, this one here.
No, like.
Oh, this one.
Yeah.
Because, right, I take my sodium, I erase it, and it has that minus sign. You see they both fall into the same category. They would actually both give me the same product whether or not there was a hydrogen or a sodium there. But nonetheless, that's why, because it has that negative charge. All right. Oh, go for it.
Oh, okay.
So in this case, they're gonna lose the hydrogen, like the other ones.
So if it has, so let's do two of them back to back here, or let's do two. So this was NaSH, and we said that the other one, and I'd actually get the exact same product if I used it, would be if I used SH2. Okay, so importantly, when it has that minus sign, that's actually easier, right? Then you just attach it as is without the charge. When it's neutral, then it's going to lose a hydrogen. So this would also give me the same product, but I've lost a hydrogen, right? It attaches as just SH, not SH2. So both of these, NaSH or SH2, will give you that same product. They both fit into that same category of strong nucleophile, weak base.
And you don't lose a hydrogen on the first one
Because it's already got a negative charge,
oh,
right? So negative charge, you don't, if it's neutral, it has to lose the hydrogen in order to, right? Because if this was SH2, you could trust me, it would have a positive charge. We have to have a neutral product, so it has to lose that hydrogen to be a neutral product.
So if you had a single hydrogen, would you lose that hydrogen attached to the S? Like single.
So you can't have just SH with no charge. That doesn't exist. So if it's just SH, it will have a negative charge. If it's SH2, then it will be neutral. So those are the only two sort of possibilities that you're going to see. Okay. All right, let's go back to this one actually, because we have our cheat sheet here. Yeah, so let's actually take our same substrate, and now we're going to toss in . Use that nitrogen one.
Is the NPO and the ETO the same thing as like RO?
Yes, exactly. Like these two kind of both belong into this category here. I'll update this and make it less confusing for that reason. Right, it really doesn't matter it's just the oxygen with the negative charge that's going to make it strong nucleophile, strong base. Right, so in this case, what's my mechanism? So this one's the E2, so I'm going to get that elimination product where this carbon is going to form a double bond with one of its neighbors. In this case, there's only one possible product, the cyclohexene. Right, notice that I've lost that chlorine, right? So there's nothing sticking out over here anymore because that chlorine is lost when I'm forming my double bond. So I start out with 1, 2, 3, 4, 5, 6 carbons on the one side. I should have 1, 2, 3, 4, 5, 6 carbons on the other side. That's another one we haven't done. Well, let's do one of these. Wait.
What's that, N3, 1 minus, look like?
Okay, specifically these two, I'm going to be honest, I put those on there because your OWL assignment will ask you, will include them, but it won't have them in any of the problems where it's asking you to draw products, just in the questions where it's asking you to identify what the mechanism is, Sn1, Sn2, E1, E2. So I kind of sort of specifically have been glossing over the structures of these. But yeah, FYI, this is what the N3 minus looks like. This one right here, you want to hate me? PHP is actually a phosphorus with 3 benzene rings attached to it.
Yeah, you won't put that on the paper. We'll spend most of the test on drawing.
Yeah, no, you don't have to draw this particular one, but that is what the it's PH3P stands for. Actually, this guy has 2 lone pairs. Also a good nucleophile. Again, this is the only problems that you'll see this is when it's asking you to identify what mechanism it is. You don't have to draw it, but that is what that big ugly thing is. All right, so let's do one more before we get done here. Again, let's utilize. right, so how many products did you draw? Awesome, yeah. So, kind of worst case scenario here, because we got a mixture of E1 and Sn1 products that we have to draw. And remember, if it's Sn1, that means I got to include both of them, where my new functional group, where my nucleophile is at a wedge, and where it's at a dash. So let's do the E1 first. Elimination, I'm going to form an alkene. The question is, where does that double bond go? It's definitely going to be between this carbon right here. But then the question is it this one? Let's actually number them. Is it between that red carbon and 1, 2, or 3? 3, right? That more highly substituted double bond. So, that is my E1 product. And again, the bigger, the more carbons, the uglier it is, right? And that's when counting carbons is just a great way to make sure that you've actually got the right thing, right? So if you ever see me doing problems, you'll see me clicking around on my paper like 100 times. I'm just counting carbons all the time to double check. 1, 2, 3, 4, 5, 6, 7, 8. All right? Just a great way to make sure that you haven't made a mistake when going from reactant to product. So there's my E1. For my Sn1, again, I'm going to have to draw both. So I'll do the one first where it's just still on that dash bond. And in this case, what am I adding on there? Just OH. Oops. And then on the other one, it's got to be on a wedge. So those are my two Sn1 products. Okay, and again, the only difference between them is in one of them I put the OH group on a dash, and the other one I put the OH group on a wedge. Cool? All right, so the only thing, so first of all, I know that this is very ugly looking stuff here. You can kind of think about it as a little bit of a puzzle, and it makes it a little bit more entertaining. All right? Your homework system is a great way to just practice this stuff over and over, right? You have these 5 problems that you have to get through to have it quote unquote mastered, but use it to also, it can regenerate a ton of new practice problems for you, right? So just continue to sort of work at it until you get the concept down. It's not so much getting those 5 problems as it is making sure you have that concept nailed down. All right, the one thing I'm going to say real quick is that you're just kind of like how I taught it, where the first thing I did was just introduce substitution reactions. Your homework's the same way, in that first homework is only talking about substitution reactions. So even in a case like this, where it's an a tertiary with a weak nucleophile, weak whatever, it's not asking you for the elimination product at all. It only wants you to draw those substitution products in that assignment that's substitution reactions. The second assignment has the mixture of the two of them together, all right? But just to point it out, the one is only talking about substitution products, okay? What was your question, sorry?
Oh, can I see the page with the cheat sheet of
Yep.
Sn1, Sn2?
Oh, this one?
Yeah.
Or this one?
That.
This one. Yeah, this is our little summary of what we did. All right, so again, next week we're going to spend Monday reviewing chapter 4, all about those aromatics. We're going to spend Wednesday reviewing this stuff, all about substitution and elimination. And then on Friday will be our second exam. All right, enjoy the weekend. You too.
Thank you.
Yeah, have a good one.